How do boundary conditions affect vibration mode shapes? Imagine plucking a guitar string and watching how it vibrates. The way it moves depends on how it is held or supported at its ends. That's what boundary conditions are all about. They tell us how the edges of a structure are fixed, supported, or free to move. These conditions have a big impact on the way structures vibrate and how their mode shapes look. Let's start with the basics. Boundary conditions describe how the edges of a structure are constrained. For example, a fixed boundary means that part cannot move or rotate. A simply supported boundary allows rotation but stops translation. A free boundary can move and rotate freely. Elastically restrained boundaries are connected to springs or flexible supports, giving partial support. These conditions set the degrees of freedom at the edges, which influence how the structure deforms during vibration. When a structure vibrates, it does so in specific patterns called mode shapes. Each mode shape is linked to a natural frequency. Boundary conditions change these mode shapes in several ways. First, they affect where the nodes and antinodes are. Nodes are points that don't move, while antinodes are points of maximum movement. For example, a beam fixed at both ends will have nodes at those ends, but a free end allows movement, changing the pattern. Boundary conditions also influence the natural frequencies. More restrictions, like fixed ends, tend to increase these frequencies because they make the structure stiffer. Less constrained boundaries, like free ends, usually lower the frequencies. This is important because it helps engineers avoid resonance, which can cause damage or loud noise. The shape of the mode also depends on the boundary constraints. For example, a cantilever beam, which is fixed at one end and free at the other, has different mode shapes compared to a simply supported beam. The number of waves or curvature in the mode shape depends on how the edges are supported. If the boundaries are elastically restrained, modeled as springs, the stiffness of those springs affects the mode shapes and frequencies. Softer springs allow more movement, making the mode shapes look more like those of free boundaries. Stiffer springs push the shape closer to fixed boundary conditions. In real-world engineering, understanding these effects is key. When designing structures like beams, plates, or machinery mounts, engineers use boundary conditions to predict how they will vibrate. This helps in locating points of high vibration, adding supports or stiffeners, and adjusting mounting points to reduce noise and prevent failure. Advanced models like Euler-Bernoulli and Timoshenko beam theories include boundary conditions to calculate accurate mode shapes and frequencies. Timoshenko theory accounts for shear deformation and rotary inertia, which is especially useful for short or thick beams with complex boundary constraints. To sum up, boundary conditions are the rules that tell us how a structure is held or supported. They shape the way a structure vibrates, determining the pattern, frequency, and behavior of its modes. Knowing how these constraints work helps engineers design safer, quieter, and more reliable structures.